This is IAT355 Visual Analytics, Lecture 2.2, where we talk about data terminology. So where we left off on the previous lecture segment, Lecture 2.1, we were talking about stages of the visualization pipeline. And so we're concentrating in this segment, in Section 2.2, Lecture 2.2, on this data transformation stage from raw information to a data set. And this slide we'd seen in the earlier segment, and I'm simply repeating it here. The overall goal, once again, is to take raw data, transform it into a form that's more workable, and in the act of doing so, what we're doing is building a model. Some of the time, we're explicitly thinking about it as a model. Other times, we're just kind of doing it as we go and not really overtly saying the word model in our minds. So now what we're going to do in this lecture is talk about terminology as we refer to data. So as I said in the previous slide, individual items are referred to cases, records, elements. Cases have attributes. An attribute is also called a variable, factor, or observation, or dimension. So let's go on to the definitions where we can talk about them more thoroughly. So here's an example of the serials data set that's available online. And we can see here that this is a table in which there are a number of columns. And this column here is the name column, the manufacturer column, calories, protein, fat, sodium, fiber, carbs, sugar, and the rest of it is cut off. What we're doing now is just simply highlighting the elements of this table and putting names to the kind of thing that that highlight element is. So this thing here, this box around the 110, this is a value. And, you know, the table has lots and lots of values, as you might imagine. The next term that I want to use is each of these things across the top are labels for a dimension. So this thing here, where Cheerios, Cinnamon Toast Crunch, Special K, etc., this thing is the name dimension. And this thing's the manufacturer dimension, the calories dimension, and so on. Also, another term that we can use here is the name property, or the manufacturer attribute, the protein variable, or the fat factor. For the purposes of visualization, these words have very, very similar meaning, but each field that does visualization might have a preferred terminology, such as factor or variable, according to the general practice of the use of information in a table like this. So for an example, a factor is a term that statisticians used, particularly in the light of experiments. So a factor might be something that has some kind of influence on the real phenomena being observed by the experiment. It might have a causation role in the actual underlying phenomena, and the statistics that will be done on the data in the table is intended to discover whether or not that factor is important to the underlying phenomena or not. Okay, next. So this entire data collection here, I've just highlighted the data itself and not the labels on the columns, is a data set. It's the entirety of the collection. And of course, the set goes off onto the right because it's cut off in this image, so you can read what I've got on the screen. Next, each one of these individual rows is a data case. It may also be called a record or an item. Record is something that you might see in database speak, and item might come from another field that is intended to get across the idea that there is a single phenomenon or a thing out in the world that has a bunch of information associated with it, a bunch of, say, attributes. And that item, in this case, Honey Nut Cheerios, has a manufacturer. It has a serving of the cereal, has a certain number of calories, a certain amount of protein, etc., etc., etc. And the entity, Honey Nut Cheerios, has a single element of each one of the variables that are listed in the table. One other thing that can be of interest is that you might also have some information about, for a particular variable or dimension, that the variable might have a number of levels or range of a dimension. So here the calories, you can see they're all factors of 10, 110, 120, 80, etc., etc. There, you don't see, 84 or 96 in here, and that might be information that might be important to the analysis in some way. Commonly, one of the variables in a table typically has the role of being a unique attribute. That is to say, an identifier for the individual item or row in a table. So here we have Cheerios. The exceptions are down here. I think these are repeated items with some variations off to the right in terms of sugar content or something like that. But for these ones here, each one of these things is a unique name for a unique cereal that has a set of unique attributes associated with it. Kind of as I've said, as we've moved along in this lecture segment, the terminology varies from field to field. So here we have a data set once again. This is a table of financial data about publicly traded companies. This is a single data case. These are the variables in the table, and this is an observation instead of a value. But other terms might be perfectly valid. This is a record with dimensions and attributes, and that's a value. So the point is that the reason why those different terminologies exist is that there are different fields of endeavor that have created their own nomenclature. And as a visualization person, you should be ready to understand what each of those terms is referring to. Okay, so the next thing to think about is when you get a data set, a data collection, a bunch of raw information in some file, there are two broad ways of looking at the information. The first is to understand what kind of information you're looking at all in the most abstract and general form. And so abstract data over here on the left is typically low-level information that tells you the barest minimum about what the information is that you're looking at. And it has things like what kind of operations you can do on it, what kind of computational functions. So for example, one of the elements in the table might be real numbers here, which might be represented as a one-dimensional floating point number, to speak computer for a second. You might have another field or another item that has a triple of values like 25500 in braces that might represent something, but that is, has some kind of usage in a different field. But one of the things that we are familiar with it is that this looks like an RGB color triple. And over here on the right is a mapping from the lower level abstract form where the numbers could mean anything to a little bit more semantically laden information in which the information is known to represent some kind of knowledge about some kind of phenomenon. So for example, 79.754 is the number of degrees Celsius, a temperature of something. And the trio of numbers here represents RGB color using 8-bit color. And typically, the conceptual type has more information about how it ought to be interpreted. And so one of the stages in data transformation is to transform this abstract, very low-level information, floating point, trio of bytes or 8-bit ints, into information about that can define what we can do with the data values in those dimensions. With just about any type of abstract data, you can identify the information. That is to say, you can identify that 79.753 is different from another value. You can typically also sort information. Even though it might not be too meaningful to sort on temperature, you can still do it. The computational capabilities are always present for you to be able to do things with. However, where the difficulty next comes is, even though this looks like a number, it might not be meaningful for you to do arithmetic on it, to multiply it by 3 or divide by 12 or subtract 2 from it. So one of the major distinctions that you can draw between different kinds of abstract data, say floats or integers or names or things like that, is the two broad categories of data that are represented by numbers, and whether the underlying information they represent is continuous or discrete. So what does continuous mean? Well, what continuous means mathematically and a little bit formally is that if you take any pair of numbers, you can always find a number in between any pair of numbers, including that pair you just found the middle of. So let's say you take 92.75 grams and 92.78 grams. You take 92 and 9.75 and 92.78, you can find a value in between them, 92.76, say. And you can find a number between 92.75 and 76. That's 92.755, etc., etc. And you can keep going infinitely. That's what it means that it's continuous. Data can take any value within the range. Let's say you've got a maximum and a minimum value for the information that you're looking at. Discrete, however, doesn't have that property. Discrete data can only take on certain values. A straightforward example is the number of students in a class. It can only be positive, and there can't be half students. You can't have 2.5 students in a class. You can either have 2 students or 3 students. Similarly with letter grades, even though they're represented by letters here, there's A, and above that is A+. There's no A and a half. There's only A and A+, and there's no values in between. Even though, as during the course of grading, I may have numeric values that I then map onto A and A+, but the grades themselves, there's no value in between A and A+, or between A and A-, and so on. So those are fundamental properties of continuous versus discrete. And the continuous thing comes from a mathematical analysis, in case you wondered. So let's now talk about the various types of data that one can find in a data set. So the first type of data is nominal data. And by nominal, think names nominal, okay? And that's data for which you can only do a very limited list of operations. You can only test for equality or inequality. Is it the same name or a different name? Is it the same address string or a different address string? And examples of that are, say, gender. Is it male or female or third gender or whatever you might choose? It's the same for student numbers. Even though student numbers look like numbers, they're a string of digits, you can't meaningfully multiply a student number by 3 and get another student number. It makes no sense to do that. In this case, student number, your student number, my student number when I was an undergraduate student, is intended to be used as a unique identifier for the student who has that number. And so testing for equality or inequality is the only thing that you can do that's sensible with it. So nominal data is a name that tends to refer to a name that refers to an individual thing, like a person's name. Closely related to nominal data is categorical data, and that is where there may be many individuals in the category. However, the test for equality or inequality thing also holds for categorical data. It's just that the usage of categorical data has the implication that there may be a bunch of things in a particular category, or indeed there might be nothing in that category also. But whereas names, we tend to think that if there's a data case, that data case has a name. And if there's no name, there's no data case. And, as might be obvious, these data are discrete. There is no idea of one name being between two other persons' name. That doesn't mean you cannot sort it, but in terms of the actual computation on the values of the names, there's no such thing as names between other names. Okay, next. The next data type is ordinal, and the way to think about that is to think ordered. This is data in which there is a well-defined order on the information in the data. And that's data for which you can only test equality and inequality, just like with nominal data, but you can also test whether something is less than another thing of that data kind, or greater than another thing. So here are some examples of that: low income, middle income, and high income, the kind of thing you might see in an economics data set, or mild, medium, and hot that you might find in a restaurant that serves spicy food. So there is a sense in that hot is more spicy than medium food, and medium is more spicy than mild food, and mild is not equal to medium, and medium is not equal to hot, but you can't multiply mild by 3 and get hot. Nor can you do arithmetic on mild. You can't get mild plus mild equals medium and a half. I'm stating these kind of silly examples basically to get across the idea that with ordinal data, you can do a little bit more than nominal data. The primary thing you can do is you can put data of these values in order from least to most or most to least, and that's it. Test for equality or inequality and put them in order. And once again, these data are discrete. There's no such thing in this little example as a value between mild and medium, given that this is the entire vocabulary of spiciness at the spicy restaurant. Next are two types of quantitative data. And we'll talk first about interval data. Now, this might seem a little bit funky, so we're going to talk it through a bit. So interval data is where there are relative measurements, but there is no fixed 0 point, and that will become clear as we talk. So in interval data, the data is numerical, and you can rank order among variables explicit between with equal distance between points in the data set. And an example of that is, say, days of the week. The minimum interval of days in the week is a single day. So you might be the same day, but if you're talking about different days, the difference between one day and another is at least 1 day. So what can you test with interval data? You can test for equality or inequality. Tuesday is equal to Tuesday. Tuesday is not equal to Wednesday. You can test less than or greater than. Wednesday, tomorrow, is greater than today, and vice versa. And you can also compute addition and subtraction. So that's another little thing that you can do above the ordinal data. So for example, let's say the interval is 2 days. 2 days added to Wednesday gives you Friday. But you cannot multiply by 2. You cannot multiply Tuesday by 2 to get Thursday or anything else, because it makes no sense. You can add days, but you can't multiply a day value to get another day. And I recognize I'm using names here, and so multiplying a name by 3 makes no sense at all already. But imagine that the day is represented by a number. So, for example, Tuesday, the day in which we're seeing this, for which this lecture is planned, is the 15th. I add 2 to get Thursday, the 17th of September 2020. But I can't multiply 15 by 2 to get anything that makes any sense, in terms of the value of the day. I'm mathematically capable of multiplying the number 15 by 2, but in terms of the meaningfulness of the day, it's not sensible. Okay. Last in the quantitative list is ratio data. And this is the numerical information that we're all used to. And ratio data has all the properties of interval data and a 0 point. And this thing is very important because what you can do is you can now do all the typical arithmetic operations. And the ratio, and why it's called ratio data, is that the ratio of two values is meaningful. Whereas with the days of the week or days of the month, say, you can't take the ratio of Wednesday to Tuesday and have that mean anything. You can't divide Wednesday by Tuesday, or Thursday the 17th divided by Tuesday the 15th. It's not meaningful. Whereas with ratio data such as weight or height or speed or velocity, you can multiply weight by some value to get another value that is sensible as a weight. So the data you can, operations you can do with ratio data is you can test for equality and inequality like before, less than or greater than, as with ordinal data. You can add and subtract, as with interval data. You can also multiply and divide in ratio data only. And so, for example, 2 times my height, whatever that is, 180 centimeters, is meaningful, and you have full mathematical operations. Unlike all the previous types, these data are continuous. And that means you could do calculus on them if you wanted to. But more important for our discussion today is that that means that there's a range of mathematical things that you can do with ratio data, with real ratio-enabled quantitative data that you can't do with interval data. One little proviso: it might be the case that you could do multiplication for continuous values, but it might in the machine be represented to some sampling level. So think about money, for example. We don't ever write a check for $8.32.8672. We write a check for $8.32, and that's it. The finer and finer details of money, the tenths of a cent, we don't do anything with. Okay, so that's still enables mathematical operations like multiplication and division to be meaningful, but sometimes there's a resolution limit below which we tend not to go, depending on what the data is about. Okay, another similar suite of categories from statistics is numerical and categorical data. So numerical is quantitative, just as you expect, and it's further divided into 2 values: continuous, which is real numbers, it's just like the ratio data we have just finished talking about, and discrete, and that's the countable things, the interval information. And in the categorical category, so to speak, we have nominal, where we can just test for equality or inequality, and ordinal, where we can put values in order. We could say that one value is greater than another. So here we go. Level of programming E is poor, is less than good, and good is less than great. Often ordinal values are sometimes recoded to be quantitative, and we can sometimes assign weights or priorities. But this statistics terminology is a little different from the terminology I just spoke of, and I'm pointing it out here just so that you're aware of what the terminology is. Okay, so hopefully you didn't fall asleep or into a coma during this section, but that's the end of Lecture 2.2, where we spoke of data terminology.